In the name of Almighty God, I am Mahsa Hassankashi, and today I want to talk about thin melting front. This example demonstrates how to model phase transition by a moving boundary interface according to the Stefan problem. A square cavity containing both solid and liquid tin is submitted to a temperature difference between left and right boundaries. Fluid and solid parts are solved in separate domains, sharing a moving melting front. The position of this boundary through time is calculated according to the Stefan energy balance condition. In the melt, motion generated by natural convection is expected due to the temperature gradient. This motion in turn influences the front displacement. In physics, chemistry, and biology, a phase transition or phase change is the physical process of transition between one state of a medium and another. Commonly, the term is used to refer to changes among the basic states of matter, solid, liquid, and gas, and in rare cases, plasma. A phase of a thermodynamic system and the states of matter have uniform physical properties during a phase transition of a given medium, and certain properties of the medium change as a result of the change of external conditions, such as temperature or pressure. This can be discontinuous change. For example, a liquid may become gas upon heating to its boiling point, resulting in an abrupt change in volume. The identification of the external conditions at which a transformation occurs defines the phase transition point, types, states of matter. Phase transitions commonly refer to when a substance transforms between one of the four states of matter to another. At the phase transition point, for a substance, for instance, the boiling point, the two phases involved, liquid and vapor, have identical free energies and therefore are equally likely to exist. Below the boiling point, the liquid is the more stable state of the two, whereas above the boiling point, the gaseous form is the more stable. Common transitions between the solid, liquid, and gaseous phases of a single component. For a single component, the most stable phase at different temperatures and pressures can be shown on a phase diagram. Such a diagram usually depicts states in equilibrium. A phase transition usually occurs when the pressure or temperature changes and the system crosses from one region to another. Like water turning from a liquid to solid as soon as the temperature drops below the freezing point. In exception to the usual case, it is sometimes possible to change the state of a system diabatically as opposed to adiabatically, in such a way that it can be brought past a phase transition point without undergoing a phase transition. The resulting state is metastable, for example, less stable than the phase to which the transition would have occurred, but not unstable either. This occurs is superheating and supercooling. For example, metastable states don't appear on usual phase diagram. And what about the structural? Phase transition can also occur when a solid changes to a different structure without changing in its chemical makeup. In elements, this is known as allotropy, whereas in compound, it is known as polymorphism. The change from one crystal structure to another, from a crystalline solid to an amorphous solid, or from one amorphous structure to another, polymorphous, are all examples of solid to solid phase transitions. The Martinistic transformation occurs as one of the many phase transformations in carbon steel and stands as a model for displacive phase transformations. Order disorder transitions, such as in alpha titanium aluminum, as which states of matter, there is also a metastable to equilibrium phase transformation for structural phase transitions. A metastable polymorph which forms rapidly due to lower surface energy will transform to an equilibrium phase given sufficient thermal input to overcome an energetic barrier. Many dynamic or soft micro porous material exhibit structural phase transition between closed and open forms. Meta-organic frameworks in particular have been extensively studied for this behavior. The phase landscape can be more complex with intermediate phases discovered. Further examples show that gas molecules can stabilize specific phases, resulting in crystal configurations that depend on the composition of the surrounding atmosphere. And what about the magnetic? Phase transition can also describe the change between different kinds of magnetic ordering. The most transition between the ferromagnetic and the paramagnetic phases of magnetic material, which occurs at what is called the Curie point. Another example is transition between a differently ordered commensurate or incommensurate magnetic structures, such as in cerium antimonal. A simplified but highly useful model of a magnetic phase transition is provided by the Ising model. And what about the mixtures? Phase transitions involving solutions and mixtures are more complicated than transitions involving a single compound. While chemically pure compounds exhibit a single temperature melting point between solid and liquid phases, mixtures can either have a single melting point known as congruent melting, or they have different liquids and solid-use temperatures, resulting in a temperature span where solid and liquid coexist in equilibrium. This is often the case in solid solutions where the two components are isostructural. There are also a number of phase transitions involving three phases: a eutectic transformation, in which a two-component single-phase liquid is cooled and transforms into two solid phases. The same process, but beginning with a solid instead of a liquid, is called a eu- eutectoid transformation. A peritectic transformation, in which a two-component single-phase solid is heated and transforms into a solid phase and a liquid phase. A peritectoid reaction is a peritectoid reaction except involving only solid phases. A monotactic reaction consists of change from a liquid and to a combination of a solid and a second liquid, where the two liquids display a miscibility gap. Separation into multiple phases can occur via spinodal decomposition, in which a single phase is cooled and separates into two different compositions. Non-equilibrium mixtures can occur, such as in supersaturation. And what about the other examples? Other phase changes include transition to a mesophase between solid and liquid, such as one of the liquid crystal phases, and the next one is dependence of the absorption geometry on coverage and temperature, such as for hydrogen on iron 110, the emergence of superconductivity in certain metals and ceramics when cooled below a critical temperature. The next one is the emergence of metamaterial properties in artificial photonic media as their parameters are varied. The next one is quantum condensation of bosonic fluid, Bose-Einstein condensation, the superfluid than situation in liquid helium is an example of this. The next one is the breaking of symmetries in the law of physics during the early history of the universe as its temperature cooled. The next one is isotope fractionation occurs during a phase transition. The ratio of light to heavy isotopes in the involved molecules changes when water vapor condenses and equilibrium fractionation. The heavier water isotopes 180 and 2 hydrogen become enriched in the liquid phase, while the lighter isotopes 160 and 1 hydrogen tend toward the vapor phase. Phase transitions occur when the thermodynamic free energy of a system is non-analytic for some choice of thermodynamic variables, for example phases. This condition generally stems from the interactions of a large number of particles in system and does not appear in systems that are small. Phase transitions can occur for non-thermodynamic systems where temperature is not a parameter. Examples include quantum phase transitions, dynamic phase transitions, and topological structural phase transitions. In these types of systems, other parameters take the place of temperature. For instance, the convection probability replaces temperature for percolating network and classifications. Ernest classifications. Paul Ernest classified phase transition based on the behavior of thermodynamic free energy as a function of other thermodynamic variables. Under this scheme, phase transitions were labeled by the lowest derivative of the free energy that is discontinuous at the transition. First-order phase transitions exhibit a discontinuity in the first derivative of the free energy with respect to some thermodynamic variable. The various solid-liquid-gas transitions are classified as first-order transition because they involve a discontinuous change in density, which is the inverse of the first derivative of the free energy with respect to pressure. Second-order phase transitions are continuous in the first derivative. The order parameter, which is the first derivative of the free energy with respect to the external field, is continuous across the transition, but exhibit discontinuity in a second derivative of the free energy. These include the ferromagnetic phase transition in materials such as iron, where the magnetization, which is the first derivative of the free energy with respect to the applied magnetic field strength, increases continuously from zero as the temperature is lower below the Curie temperature. The magnetic susceptibility, the second derivative of the free energy with the field changes discontinuously. Under the Ernst classification scheme, there could in principle be third, fourth, and higher order phase transitions. For example, the Gross-Witten-Wadia phase transition in second order lattice quantum chromodynamics is a third order phase transition, and the Tracy wisdom Witten distribution can be interpreted as a third-order transition. The Curie points of many ferromagnetics is also a third-order transition as shown by their specific heat having a sudden change in slope. In practice, only the first and second-order phase transitions are typically observed. The second-order phase transition was for a while controversial as it seems to require two sheets of the Gibbs free energy to oscillate exactly, which is so unlikely as to never occur in practice. Cornelis Gorter replied the criticism by pointing out the Gibbs free energy surface might have two sheets on one side, but only one sheet on the other side, creating a fork appearance. The Ernst classification implicitly allows for continuous phase transformations where the bonding character of a material changes but there is no discontinuity in any free energy derivative. An example of this occurs at the supercritical liquid-gas boundaries. The first example of a phase transition which didn't fit into the Ernst classification was the exact solution of the Ising model discovered in 1944 by Lars Onsager. The exact specific heat differed from the earlier mean field approximations, which had predicted that it had a simple discontinuity at critical temperature. Instead, the exact specific heat had a logarithmic divergence at the critical temperature. In the following decades, the Ernst classification was replaced by a simplified classification scheme that is able to incorporate such transition. Modern classification. In the modern classification scheme, phase transitions are divided into two broad categories, named similarly to the Ernst classes. The first order phase transitions are those that involve a latent heat. During such a transition, a system either absorbs or releases a fixed and typically large amount of energy per volume. During this process, the temperature of the system will stay constant as heat is added. The system is in a mixed phase regime in which some parts of the system have completed the transition and others have not. Familiar examples are the melting of ice or the boiling of water. The water doesn't instantly turn into vapor but forms a turbulent mixture of liquid water and vapor bubbles. Joseph Emery and Mikhail Vortis showed that a quenched disorder can broaden a first-order transition, that is, the transformation is completed over finite range of temperatures, but phenomena like supercooling and superheating survive and hysteresis is observed on thermal cycling. And next one is second order phase transition. Second order phase transition are also called continuous phase transition. They are characterized by a divergent susceptibility, an infinite correlation length, and a power law decay of correlations near critically. Examples of second-order phase transitions are the ferromagnetic transition, superconducting transition for a type I superconductor. The phase transition is second order at zero external field, and for a type II superconductor the phase transition is second order for both normal state mixed state and mixed state superconducting state transition and the superfluid transition. In contrast to viscosity, thermal expansion and heat capacity of amorphous materials show a relatively sudden change at the gas transition temperature, which enables accurate detection using differential scanning. Colorimetry measurement and Lev Landau gave a phenomenological theory of second-order phase transitions. Apart from isolated simple phase transitions, there exist transition lines as well as multi-critical points when varying external parameters like the magnetic field or composition. Several transitions are known as infinite-order phase transitions. They are continuous but break no symmetries. The most famous example is the Kosterlitz Toulouse transition in the two-dimensional XY model. Many quantum phase transitions, for example in two-dimensional electron gases, belong to this class. The liquid-gas transition is observed in many polymers and other liquids that can be supercooled far below the melting point of the crystalline phase. This is uh, atypical in several respects. It is not a transition between thermodynamic ground states. It is widely believed that the true ground state is always crystalline. Glass is a quenched, disordered state and its entropy, density, and so on depend on the thermal history. Therefore, the glass transition is primarily a dynamic phenomenon. On cooling a liquid, internal degrees of freedom successively fall out of equilibrium. Some theoretical methods predict an underlying phase transition in the hypothetical limit of infinitely long relaxation times. No direct experimental evidence supports the existence of these transitions. And what about the characteristics, properties, phase coexistence? A disorder broadened first-order transition occurs over a finite range of temperatures, where the fraction of the low temperature equilibrium phase grows from 0 to 100% as the temperature is lower. This continuous variation of the coexisting fractions with temperature raises interesting possibilities. On cooling, some liquids vitrify into a glass rather than transform to the equilibrium crystal phase. This happens if the cooling rate is faster than a critical cooling rate and is attributed to the molecular motions becoming so slow that the molecules cannot rearrange into the crystal positions. This slowing down happens below a glass formation temperature Tg, which may depend on the applied pressure. If the first order freezing transition occurs over a range of temperatures and Tg falls within this range, then there is an interesting possibility that the transition is arrested when it is partial and incomplete. Extending these ideas to first-order magnetic transition being arrested at low temperature resulted in the observation of incomplete magnetic transitions, with two magnetic phases coexisting, down to the lowest temperature first reported in the case of a ferromagnetic to antiferromagnetic transition. Such persistent phase coexistence has now been reported across a variety of first-order magnetic transitions. These include colossal magneto-resistance magnetite materials, magnetocaloric materials, magnetic shape memory materials, and other materials. The interesting feature of these observations of Tg falling within the temperature range over which the transition occurs is that the first-order magnetic transition is influenced by magnetic field, just like the structural transition is influenced by pressure. The relative is with which magnetic fields can be controlled, in contrast to pressure, raises the possibility that one can study the interplay between Tg and Tc in an exhaustive way. Phase coexistence across first-order magnetic transitions will then enable the resolution of outstanding issues in understanding gases. Critical points in any system containing liquid and gaseous phase there exists a special combination of pressure and temperature, known as the critical point, at which the transition between liquid and gas becomes a second-order transition. Near the critical point, the fluid is sufficiently hot and compressed that the distinction between the liquid and gaseous phases is almost non-existent. This is associated with the phenomena of critical opalescence, a milky appearance of the liquid due to density fluctuations at all possible wavelengths, including those of visible light. And what about the symmetry? Phase transitions often involve a symmetry breaking process. For instance, the cooling of a fluid into a crystalline solid breaks continuous translation symmetry. Each point in the fluid has the same properties, but each point in a crystal doesn't have the same properties unless the points are chosen from the lattice point of the crystal lattice. Typically, the high temperature phase contains more symmetries than the low temperature phase due to the spontaneous symmetry breaking, with the exception of certain accidental symmetries. For example, the formation of the heavy virtual particles, which only occurs at low temperatures. And here we are. There is a Comsol simulation, and the component you see the geometry. It's a simple two-dimensional geometry uh, with a different boundary conditions. And we go through the parameters that I have defined: thermal conductivity, a specific heat capacity, coefficient of thermal expansion, kinematic viscosity, density, latent heat of fusion, melting point, hot well temperature, cold wall temperature. Here you can see the material that I have applied is a tin as a two-phase of liquid and solid. And the physical module that we have selected is the form geometry, heat transfer in solid and fluid because we have a solid and liquid, laminar flow, and the multiphysics. The difference between solid and liquid is between the thermal conductivity and their heat capacity. You see the deforming domain, that the mesh smoothing type is by Laplace functionality, and the prescribed normal mesh displacement, because we have a mesh displacement, as you can see that after pressure we have the stress, the temperature fluid. You see that this boundary condition has been changed, while we had a straight line here that separated two parts of this rectangle. There is a square here, and we have separated by a line to two different rectangles, and we use the deforming domain and prescribe a normal mesh displacement. But you can see that we have a prescribed normal mesh displacement by uh, choosing the 0, and everything else is by default. And you can see the temperature. There is a change. This change is because of heat transfer, because we have an inlet and outlet. We have a solid and fluid section. You see that this part is a solid section, and the left side is a fluid section. We have a two different temperature 1, temperature 2. You see that the temperature 1 is TH and temperature 2 is TC, that we have defined in the parameter table. TH 508 Kelvin, and TC at the solid side is 503 Kelvin. You see that in the solid side we have a cooler temperature, and you see that we have a cooler temperature is 503 Kelvin, and here in the liquid or fluid side we have a 508 Kelvin. And we go through the velocity. This velocity comes from the laminar section, and we have defined the gravity, also the wall fluid properties, and also the pressure point constraint. And now you can see the deformed geometry. It's by rectangle. The elements that we have chosen here is by a rectangle here, and temperature and fluid. You see that how much is different. It's temperature and it's the velocity, and also there is a pressure here. If you see, the pressure is based on Pascal. At the top we have a high pressure, and at the bottom we have a negative pressure. Thank you so much for watching my tutorial video until the end, and also you can download this Comsol simulation by the name of Team Melting Front from my github.com/mahsa script.